So to get a little bit of variety, both for you, the viewer, and myself, I'm now sharing a screen here of 3 quadratic equations to solve by completing the square. Remember, the 2 steps we had at first were that we have to have all the terms with x on one side and the constant term on the right side of the equal sign. We also need to have a 1x squared. Now, this first one, we've already got the 1x squared, but we do not have all of the x terms on the left side and the constant on the right-hand side. So I'll add 3x first of all. So now we have this. By the way, this one could be solved by factoring, if I remember right, but the 2 after that would not be something we could solve by factoring. Next, I'm going to add the 28 to both sides. Feel free to continue to draw the picture like what we saw yesterday, like we saw in the earlier examples, where we had something like that showing. But I'm going to show just the arithmetic for the side work in these 3 examples. So we have we already have the 1x squared, so it's okay to, first of all, take half of the 3. And we're not going to get something that reduces as nicely. Just going to leave that as 3 halves then. And then we square it. Which will give us, since we can, again, for lack of a better word, distribute the squaring across the division that we have here. Got 9/4. So 9/4 will have to be added to both sides. Now that might look a little bit intimidating, but 2 things about this. First of all, if we multiply the 28 by 4, which should get us 112, we've got a common denominator there. And on the left-hand side, not much thinking has to be done, because the second step of the side work here told us what we were going to add to both sides. And the first step tells us something about what we have when we are writing the perfect square trinomial on the left side as a binomial squared. It's going to be x plus 3 halves. And on the right side, since I got a common denominator, adding 112 plus 9, we've got 121. So now we can apply the square root property. And again, it's just going to cancel the squaring on the left side. Don't forget the plus or minus sign. Square roots of 121 over 4. Well, we can split up that division across, split up the square root across the division, and we'd have square root of 121 is 11, and the square root of 4 is 2. So give me a moment, it'll come up in a minute. We can split the square roots across the division, and that the square root of 121 is 11, and the square root of 4 is 2. Notice how we're getting the same denominator. If you are not, that should be a sign that something is going wrong. I'm going to isolate the x by subtracting 3/2 from both sides. And because we completely got rid of the square root, we should split that into the two cases of plus or minus. So with the negative 3/2 minus 11/2, we would have negative 14/2, or negative 7. And with the addition case, negative 3/2 plus 11/2, we would have 8/2, so positive 4. On that one, if you had simply factored, you would have had x plus 7, that quantity, times x minus 4. At this stage right here, the quantity x plus 7 and the quantity x minus 4, so that you would get, after applying the zero factor property, x equals negative 7 and x equals 4. No surprise. Well, based on the examples we've seen so far, and this one, I can tell you two things. One, when I have my choice, if the directions don't state which method to use, then if we already have a 1x squared and an even coefficient for x to the first, or if I can easily get a 1x squared and then come up with an even coefficient for x to the first, then that's when I like to apply completing the square, if it doesn't occur to me pretty quickly how I would factor something. So actually that's what we have in this next case. I'm going to add the 71 to both sides. For side work, I would have the coefficient of x to the first is 4. We will divide that by 2 to get 2. And we have to, whoop, don't know how that happened. We have to square that 2 to get 4. So we're going to be adding 4 to both sides here. On the left-hand side, that'll give us a perfect square trinomial that we can write as a binomial squared. And on the right, we've got 75. So Remember, the second step of side work was telling us what we had to add to both sides, the 4. The first step of side work is showing us what we need inside the binomial for the binomial squared. Since that was a positive 2, then this is a positive 2. On the previous one, since that was a positive 3/2, here we've got x plus 3/2. So let's see here. Apply the square root property, and we're going to have x plus 2, since on the left-hand side, that's going to cancel the squaring. And on the right side, we'll have the square root of 75. And again, if we were together as a class, hopefully somebody would go, wait a minute, you forgot the plus or minus sign. And let's try that again, plus or minus. There we go. Okay. So I'm going to isolate the x by subtracting 2. And although 75 is not a perfect square, there is a perfect square factor other than 1 that goes into it. So I'm going to break up 75 as 25 times 3. So we'll have 25 times 3, split up that square root across the multiplication, and we'll have the square root of 25 is 5, while the square root of 3, there's no perfect square factor that goes into that besides 1. And so this is how we would have to leave it. Again, on MindLab Math, you may need to, if they don't let you use the plus minus sign, you may need to type the 2 separate cases here with a comma in between, looking something like that perhaps. And for our third example, though not our final example of this section, because I want to show an application question or two, here we have the terms with x alone on the left side and the constant term alone on the right side. I'm going to have to divide everything by 3, which would give us x squared plus 7x equals 17. And then we do our side work here. Take half of the coefficient of x to the first, that is 7, half of 7, 7/2. No need to write this as a decimal because it's not difficult to square something that's over 2. And if you leave it written this way, distributing the squaring across the division, 7 squared is 49, and 2 squared is 4. That's telling us what we're going to add to both sides. And if we just look at the 7/2, that'll tell us what we need to see along with x when we rewrite the perfect square trinomial as a binomial squared. So adding 49/4 to both sides. On the right side, I'm going to get a common denominator of 4. So multiply 7/1 by 4/4 to get 68/4. And on the left side, remember our first step of the side work, since that was a +7, that first step we've got +7/2. Then what we're going to see when we rewrite the left side as a binomial squared is x plus 7/2. (68 plus 49 is 117. Apply the square root property, which is going to cancel the squaring on the left side. Plus or minus the square root of 117/4. And that was supposed to go inside of the square root. Come on. Isolate the x by subtracting 7/2. Split up the division underneath the square root. And the square root of 117, we have to work on simplifying that, but the square root of the 4 in the denominator is, of course, going to be 2. So again, a good thing that after that we've got the same denominator. Let's see here. (117), the largest perfect square that'll go into that, I believe, is 9, and that it would go in 13 times. Nine times 13. Well, 9 times 10 would be 90, and 9 times 3 would be 27. So 90 plus 27 would be that 117. So we would take the square root of the 9 and the square root of the 13. The 13 we can't simplify any. but we can take the square root of the 9. That will give us 3. Noting that we have a common denominator, you may be expected to write this as a single fraction. It's also worth looking into whether or not you can reduce, but 7 over 2 and 3 over 2, those cannot be reduced. So here is what we would have. Again, on MyLab Math, if they don't let you use the plus minus, then you'd have -7 minus 3 squared of 13 all over 2, and comma, -7 plus 3 squared of 13, all of that in the numerator, all over 2.